Everybody, good morning, good afternoon, and thank you so much for joining this demo session. This is the topic is simplified AI model deployment with Triton Inference Server, and we have our team here. So let me. Okay. So myself, my name is Shankar Chandrasekharan. I'm in the NVIDIA product marketing team. And Davide, you want to introduce yourself?
My name is Davide Onofrio. I'm an NVIDIA deep learning engineer working in the technical marketing engineering. Abhishek?
Thank you, Davide. Hi, guys. My name is Abhishek. I'm also a deep learning engineer working in the technical marketing team. Mahan?
Hey everyone, this is Mahan Salehi. I'm the product manager for the Triton Inference Server, which is an open source inference serving software that we'll be discussing with you guys today.
Yeah, thanks, Mahan. Thanks, everybody. So before we get to the demo, I think we'll quickly talk about, give an overview of Triton itself, and then, so Mahan and I will basically tag team here, and then Davide and Abhishek will basically go through the demo itself. And then finally, we'll have definitely time for questions and answers. Okay. So before we get in, look, what is Triton, right? So let's look at what are the challenges in model deployment. In a typical AI lifecycle, there's the data scientist and the researchers have developed the model, and the engineers are now have made it production ready. Now it's time to actually deploy the model. Now, there are actually deploying models is quite hard and complex because of these reasons. The number one is just multiple frameworks. People have choice, so they use different types of frameworks like TensorFlow, PyTorch, or OpenVINO or custom, and there are different ways of deploying them. So these each framework requires its own serving, serving backend. And this combination or this multiplicity of frameworks is definitely one challenge that people see in production, because it requires either supporting all those different backends or requires retooling in production. The the second challenge would be just different types of queries. The models are all different. They're all designed for different use cases. Some might require real-time response. Some might be used in an offline batch scenario, and some might require streaming input. Some might require like a pipeline of logic, like models working together to solve the inference. So these different types of queries, they all need different types of optimization for a very efficient inference in production. The third challenge is third and fourth related to the cost itself. There is a need for a mixed infrastructure, meaning the inferences, some inferences can run on CPUs, some need GPUs, and again, it can run on a cloud or data center, or it could be on an embedded device. And there's different deployment environments. If different solutions, disparate solutions are developed for each one of them, that actually increases the cost of overall inference deployment and model deployment. The other challenge related to cost is inference is typically a scaled activity, or it can scale pretty quickly, and there is a need for very high performance and in some cases very low latency, right? Regardless of whether the inference happens on GPUs or it happens on CPUs. Now, if the underlying hardware, which is the GPU or the CPU, if they aren't utilized enough, then the performance is not obtained. And at the same time, the underutilization increases the cost of the overall deployment itself. The last but not the least is the ecosystem tools. As I mentioned, inference is where AI actually is being deployed, and that's where the value of AI comes out for the business, right? And in a production environment, there is generally a whole set of tools and software platforms that are in play here. Like, for example, you have if it's a cluster, you have a cluster orchestration tool, or if there's a scaling tool, or if there's a monitoring tool. So there is a standard set of tools that are used in production, whether it's in cloud or on premises. If the way that the software that's used to deploy these models, if it does not work with that standard ecosystem of tools that is already in production, now that can lead to this inefficient implementation or non-scalable, and in the long run, it's going to be harder to maintain and costly to run the inference itself. So these are the challenges that we see in model deployment. And so now Mahan can actually, can walk us through like what Triton is and how Triton helps address these challenges.
Thanks, Shankar. So as we mentioned, those are the challenges that we just summarized are the biggest pain points that we've seen organizations face and developers face in deploying their models in production. And so we started building Triton to address those pain points over 2 years ago now. So it's a very mature software, and again, open source. So it's all available for you to look on GitHub. And we created Triton to hopefully make it easier for everyone to deploy their models in production. And so here we wanted to highlight and showcase some of the key features and benefits. And so we'll start by first showing that Triton supports multiple different framework backends for your model. And so you might be having models that are trained and developed with TensorFlow, with PyTorch, Onyx, TensorRT, which is NVIDIA's optimizer and runtime engine for deep learning models. And then OpenVINO for inferencing on Intel CPUs, and also even custom backends, which you've created specifically for special types of models and frameworks. And in Triton, we have support for all of the above, and those come pre-shipped with the Triton container every month. So if you're a developer and you're interested in creating your models in different backends, you no longer have to worry about creating separate inferencing solutions for each framework or each type of model that you're deploying. The other key advantage of Triton is having support for mixed infrastructure, as Shankar mentioned. So we see models today are being deployed on different types of environments and different types of hardware. And Triton from the very beginning was designed to support being able to deploy on GPU and CPU as well. We've also designed it to be able to allow you to launch models in different deployment environments, whether that's in the cloud, in the data center, at the edge, and in embedded devices, and on bare metal and also virtualized environments. And so the idea is you can have a single standardized inference API that allows you to be able to deploy models from multiple different frameworks on GPU and CPU and in different deployment environments. Now, the other key advantage of Triton is that it has support, not only support, but also optimizations for different types of inference queries that might be coming in. And so with real-time predictions, your focus is on minimizing latency and getting responses as fast as possible within some cases. On the other hand, you might have applications or use cases that require you to do offline batch inferencing, where your priority is to maximize throughput. And then there's streaming applications like conversational AI or video analytics. And finally, a lot of use cases today require support for model ensembling. And that's the idea of being able to chain multiple different models together into a single pipeline, or different pre and post-processing operations around your neural networks that are all chained together. And the idea is that with Triton, we have features and optimizations for each of these different types of use cases. And we have customers that have deployed Triton in production for real-time inferencing use cases, offline batch. We have built-in support for audio streaming inputs and also integrations with other NVIDIA products for video analytics use cases. And then finally, we have an ensembling feature in Triton that allows you to be able to create pipelines of multiple different models and pre- and post-processing operations. And then lastly, the final key advantage that I wanted to share here on this slide around Triton is the features that we have that allow you to maximize your hardware utilization of your CPUs and GPUs to get the best possible performance, but ultimately translate that to lowering the cost of production deployment. And so in particular, we have two features in Triton that allow us to be able to maximize utilization to get higher throughput. And the first is the idea of concurrent model execution. And that's the idea that rather than loading a single model to run on a single GPU or a single model to run on a single CPU, Triton allows you to be able to create multiple copies or multiple instances of your model to run simultaneously on one GPU or CPU. And so that way, you can make use of much more of the space that's available on your hardware and utilize it even more and get better performance. The other feature that we have for maximizing performance is called dynamic batching. And that's the idea that as independent inference requests are coming into Triton, on the server side, Triton can group those requests together dynamically within the server to create one larger batch to execute inference on. And so if you have multiple different clients that are sending in multiple independent requests to Triton, on the server side, we can group them together and get a better performance and efficiency through running inference on a batch. And at the same time, this dynamic batching feature is very configurable, so you can specify a latency limit or a threshold for how long Triton should wait in order to create these batches. And so that way you can maximize performance while still staying within your latency constraints. So now I'll pass it back to Shankar for the other features.
Yeah, thanks, Mahan. I think this is great. So the other set of features, I think this is very relevant to the audience here is how does Triton work with the other ecosystem of tools that are being used for AI and application deployment? Yeah, first is Kubernetes is what we see most organizations use for deploying their applications. And Triton has a very deep integration into the Kubernetes ecosystem itself. So Triton is available as a container from NGC. So as a container, it fits very nicely into your microservice architecture, and Kubernetes can be used to scale the Triton container for your inference deployments. And it can be used with any Kubernetes distribution on both on the public cloud and on premises. And specifically, we have also done integration with KF serving. KF serving is the serverless inferencing on Kubernetes, and the KF serving actually can be used with Triton for actual inference serving. That's on the Kubernetes side. Now, on the MLOps specifically, where we look at the automating this end-to-end workflow, Triton has some very key features like live model updates. So while Triton is out in production deploying, serving these models, the models, let's say, are updated based on a new data or a new algorithm. They can be updated in Triton without restarting the application or without restarting your service itself, right? So that's so you basically are getting zero downtime into your production. And also Triton supports dynamic model loading, unloading. What if you have hundreds of models, but you're only using a few of them at a time, right? Depending on the application. So Triton can, there's a model control API that can be used to load and unload models dynamically, so that the models that are needed is what's running currently in the GPU or CPU. And finally, there's a Triton model analyzer. I think there's a very rich functionality that complements your serving, is where before you actually go into production, a model analyzer is a tool that can be used to basically characterize your deployment. Meaning, if you have a target GPU or CPU, you can figure out, okay, how many models can I put in at a time? How much is the memory consumption? What's going to be the throughput? What's going to be the latency? So you can characterize all these things for a given model, for a given target deployment. And based on that, you will have a very efficient serving infrastructure. And to make it easy, we are integrating Triton into all other, into some of the standard MLOps platforms that people use. For example, Triton can be used in Google Cap, or they now rebranded as a Vertex AI. It can be used in SageMaker. It's part of Azure. It's natively part of Azure ML pipeline. And also some of the other providers like Selden and ClearML have integrated Triton as part of their offerings as well. And as Mohan said in the beginning, this is open source. Triton is completely open source, so you can inspect, customize, extend it. And even if you're using it as a container, it's customizable. You can start off with a very, I would say, a small memory footprint, and then with the required functionality, and then you can add modules to it as you grow. So as Mohan said, it's a mature product. A lot of organizations use Triton for a variety of use cases. A few of them you can see on the slide here by different companies. And as I mentioned, it's got a very neat integration into the Kubernetes ecosystem, both on the cloud on-prem, and of course we are doing integrations into the cloud AI platforms and MLOps platforms too. So with that, I'm going to pass this on to Davide, and Davide is actually going to walk us through the demo.
Yes, thanks, Shankar. So let me introduce, before Abhishek will go through the demo, let me introduce what we are going to see. So could you go on to the next slide, please? So the demo we are going is part of a bigger system. We integrated a recommender system into MLOps pipeline. In particular, the recommender system that we are using is based on NVIDIA Merlin. And this is not the focus of this session demo. So I will just give a little introduction on Merlin. Because what we want to focus here is on the inference part of the recommender system, which is based on Triton. But NVIDIA Merlin is basically made of three main components. NV Tabular, which is basically deals with data preprocessing and data loading. UHCTR, which is the component to train a recommender system. And basically Triton, which is the part that runs inference. Next slide, please. So as I said, the recommender system here that we integrate in this MLOps pipeline is just an example of how you can use and integrate Triton in your MLOps pipeline. Here we see overview of the system we integrated, and let me describe a little bit what is in the pipeline and which part are we going to focus in the demo. So starting from the data store, data for the recommender system is preprocessed by NV Tabular, which is part of Merlin, as I was saying before. Data features are extracted and stored in a feature store. Then they are ready to be processed and used to train from the UHCTR. Once the model is ready, is trained, it's going to be evaluated in a different component. Then, once the model passes the evaluation, is sent to the model repository. The model repository is connected to a deployment component that is basically responsible for deploy the model to Triton. Triton runs inference and send inference to the client through through gRPC or HTTP endpoints, as we seen before. This data, together with the reply from the client, is used to monitor model drift, which means that once you can monitor actually how the model is performing, how your recommender is performing. If deviates from the expected performance, with this model drift monitoring, you can trigger a new retraining with the new data that is coming from the client. So the implementation of this system is done in making use of Kubeflow, but it's not. It can be extended to other frameworks. Next slide, please. So the scripts, the source code for deploying this system are available on GitHub. You can find the link at the bottom of this slide. If you are interested in the details, what you are going to see is we will focus on the inference part, but this system will show the persistent volume for moving large amount of data, like the one required in the recommender system. We are, as I said, we are going to use a Kubeflow pipeline demonstrated in this case on A100 GPUs. A100 are the latest architecture of GPU from NVIDIA. And they're actually very useful because a single GPU can be split up to 7 smaller GPU and increasing, therefore, their utilization. You are going to see also in the script that we are releasing continuous training, meaning that in this case, for example, a recommender system is a system that needs often retraining. So through the triggers and through the mechanism of the MLOps system that we released, you can see how a model can be retrained and continuously using the freshly available data. We're going to see in the demo also auto-scaling, meaning that the inference part can scale depending on the request of the amount of the number of requests coming from the client. We can scale up and down the Triton server easily, thanks to the metrics that Triton exposes. Again, this is not the focus of this demo session, but the source will also explain how to use Merlin, the recommender system. Again, a 100 MIG is the single slice of the GPU when you split the GPU. And then, and this is, we will see this in the demo, how we can monitor performance, drift, and outlier of the inference results. Okay, again, on the bottom of this slide, you'll find the link to the source, to the scripts. But now it's time for the demo. Abhishek, you ready?
Okay.
So, yes.
I'll stop. Yeah, go ahead.
I'll share my screen. Yeah. Thanks for attending the session, everyone. So as you saw, a recommendation system is a perfect use case for MLOps pipeline, mainly because it requires continuous training along with continuous integration and continuous deployment. So for training for having the pipeline which performs continuous integration, deployment, and training, we decided to go with Kubeflow because it has easy to use an API as well as good integration with GKE. So as you can see on my screen, this is the GKE Kubernetes engine window. We have a cluster running called Merlin KF demo here with 3 nodes, 2 A100 nodes and a CPU node. To run the pipeline on Kubeflow, you need to have this cluster ready. You can go to the Kubeflow pipeline getting started page for more information. I already have uploaded our demo pipeline that we use for the demo. So this pipeline basically consisted of components. Each component has a container packaged into it, and all the codes, the scripts are packaged into that container. So as we go from the start, we start with the data extraction process once we have the data. So for our use case, we use the Criteo 1 terabyte click database dataset. It has multiple Parquet files which are used for training the model. So the first component is data extraction, which extracts the data from the database basically from Google Cloud Storage into a persistent volume. This persistent volume is used mainly for data transfer between these components, as the data is quite large. The second component is to validate the data. So in the first run, we extract some statistics from the database and store those stats in the persistent volume. In the subsequent runs of the pipeline, we check whether the new incoming data stats match with the original training data or not. Because in the case of recommendation systems, the real world data might change, the trends might change, right, as time progresses. Once we validate the data, we pass it to the training component, which does both pre-processing on the data as well as training using huge CTR. Once the model is trained, checkpoint is stored in the persistent volume, which is then accessed by the Triton inference server. So Triton loads the huge CTR trained model and keeps it ready for inference from the client. One thing to take care of is that Kubeflow pipelines are not persistent, but we want our inferencing solution to be persistent even after the pipeline ends its execution. So Triton Inference Server is deployed in GKE rather than just running it in the Kubeflow pipeline. And the last component in this pipeline is data monitoring. This is mainly used to monitor the incoming data and the model performance. So whenever the model performance drops, the pipeline is triggered again, and it starts retraining the model with the new data. So we can go ahead and create a run here. You can add all the description, the settings. One good thing about using Kubeflow is that it has both options. You can have one-off pipeline or you can have a recurring pipeline. So recurring can be a periodically triggered pipeline, which does continuous training over time. But in our case, we used a triggered pipeline based on the metrics of the model performance. So if the model performance dropped, we triggered the pipeline again. So just for the demo purpose, this is how the blocks run. For the demo, I have not included the scripts here because it does take some time to load the data and to train the model. But you can see all the metadata information about all the components over here. So once the pipeline runs, it deploys the Triton Inference Server on GKE, basically on A100 nodes. So on the GKE console video, the terminal, you can check whether the Triton pod has been deployed or not. So it will be kubectl get pods. Yeah, here we see that the Triton Inference Server pod is deployed and it is running on GKE A100 node. Describe. So you can get all the metadata information about this Triton pod running. And as you can see, it is running on the A100 pool here. So I have two A100 nodes running on this cluster. And the Triton has been deployed, and it finds the model repository in the persistent volume and loads the model repository and makes it ready for inference here. To get the external API for clients to communicate with the Triton server, we need to find the external IP, which this external IP is basically exposed by the load balancer that comes with the Triton Inference Server itself. So we have a Triton Inference Server GitHub page. Here you can find all the information on how to use the Helm chart and how to deploy it on any of the cloud providers or even on-prem machines. So we'll get this IP, and let me call the IP from my client. So this client is running on my, this is just running on my laptop. I'm communicating with Triton server hosted on GCP by providing the IP port and the API. So as you can see, it has connected and it returned 200 OK. So now the clients can start sending inference requests to the Triton server running here, right? So I have a Triton perf analyzer. This perf analyzer also comes with Triton Inference Server client Docker containers. So this is basically to test the Triton deployment. You can specify the model, specify the IP, and also the concurrency. So the concurrency specified here, which is from 30 to 40, sends concurrently 30 inference requests at time t equal to 1, and then keeps on incrementing it till 40. So it's a variable which you can use and change. And once this perf analyzer runs, it will keep printing logs and give you stats about latency and throughput as well. A good thing about using Triton is that it exports GPU metrics. So if I go back here and ask for GPU metrics, it exposes the metrics at port 8002. So this will print all the GPU metrics you might require to monitor the performance of the GPU and Triton server as well. So one can export these metrics to Prometheus and check it on Grafana. So I have a Prometheus instance running. Yeah, so we can view all these statistics over here. So these metrics are exported by Triton server. As you can see right now, when we started the client is sending inference requests to the Triton server for the recommendation system. And as you can see here, the cumulative inference request has started going up. And also the queue time of the inference requests coming through, right? So this brings us to the next point about auto scaling. So Triton, because it is containerized and running in a pod, it can be auto-scaled using horizontal pod autoscaler on GKE or any other Kubernetes instance. So I have the autoscaler running here. So this autoscaler is looking for the queue time of the incoming request. So average queue time of the incoming request over time. So if this queue time goes over a threshold, which is 200 milliseconds that I specified for deploying the HPA, if this goes over 200 milliseconds, then it starts to spin up a new Triton pod server. So basically, it scales the Triton pod horizontally. I'll have to increase the... Yeah. So once the Triton pod goes on, once the inference queue time goes on increasing, and if it goes beyond the threshold of 200 milliseconds, Kubernetes HPA will automatically start up a new instance of Triton server, and we'll be able to see it over here. So right now, the Triton is handling incoming inference requests quite quickly. So the queue time has not increased much, and only one instance is running. So let's give it some more time. Also, so this is the perf analyzer, which keeps sending inference requests. But along with this, we also have a client application, which checks the model and sends inference requests for in batches and gets an accuracy score as well. So as you can remember, in the pipeline, we had the monitoring module, which monitors this ROC AUC score of the model. And if this drops below a certain threshold, so right now this is 0.7, if it drops below a certain threshold, it will trigger the Kubeflow pipeline again. So once the Kubeflow pipeline triggers again, it will extract the newly sent data, which gets stored automatically in a GCS bucket. It will validate the data, pre-process, and train the train the model again. Once the model is trained, we don't have to start up Triton inference server again because it's already deployed on GKE. So a good thing about Triton is model versioning. Once you have a new version of the model, you can directly copy it in the model repository, and Triton will pick up the new model right from there. Okay. Yeah. So as you can see, the horizontal pod autoscaler kicked in and started a new instance of Triton here. So this new instance of Triton is also taking in the incoming request. So basically the load is being balanced on multiple instances, and hence the queue time will reduce. So if you can see the graphs here, it will start populating the graphs. There is a new instance started by the horizontal pod autoscaler, and the energy consumption of that instance, the second node, has gone up. So this will show up as time progresses, and the average queue time will go down because the load is being balanced, basically. Another great new feature about Triton is the model analyzer. The model analyzer gives a good statistics about the model, and it will show up how the model can be deployed in Triton before going into production. So basically, the batch size, the latency requirements, and other information. It's a pretty handy feature, and it comes with a Helm chart as well, which can be deployed on GKE. So I will close the client. Install. And model analyzer. So model analyzer has been deployed, and you can see a pod running. Yeah, here. So right now, the Triton inference server is occupying the GPU on A100 instance. Right now, it is terminating because I uninstalled via Helm chart. Once it terminates, we'll have a free GPU, and the model analyzer will start running here, as you can see. The model analyzer will print out logs. Yeah. So as you can see, it will find the GPU instance. It will find the model repository in the PV. So I have specified the correct path location in the Helm chart, and then it will start collecting the statistics. This takes a while to run because the models are huge. This will create multiple instances with different batch sizes, and then print out the statistics like you have on the GitHub page here. And this is a pretty handy tool before actually deploying the service into production. Yeah, I think that's it from the demo from my side. Thank you.
Thanks, Abhishek. So, WD, we have a few questions on the chat.
Maybe just before diving into the Q&A, one last thing to mention is in terms of where you can find Triton today, there's two paths. So it's all open source, so you can find all the code and documentation on our GitHub repo. And we'll share a link to that in the chat as well. The other path is that Triton is available as a Docker container, which you can run as a microservice on GKE, as Abhishek is showing, on Kubeflow, any other container orchestration platform that you're interested in. And so where you can find that Docker container is on the NGC, or NVIDIA GPU Cloud. It's where we host our containers for different products, including Triton. And so you can pull it from there. And we have a monthly release cadence for Triton. So every month, at the end of the month, we drop a new Triton container and a new version on our GitHub, which has new features and updates. So make sure to check out the latest one.
Great. Thanks, Mohan. All right, so let's go through the questions. This question on, why not just use Kubeflow instead of Triton? So Triton is actually part of Kubeflow. So if you look at Kubeflow Kubeflow gives you the flexibility of using different serving solutions. It supports multiple different serving solutions, and Triton is part of it. So if you're using Kubeflow, you can use Triton. And Triton is also part of KF serving. So if you're using KF serving, you can use Triton as part of KF serving too. So it is definitely part of your Kubeflow.
Yeah, the way to think about it is that Triton is the inference serving backend that Kubeflow or KF serving uses to actually run inference on your models. But then KF serving, for example, has a lot of other features outside of model inferencing or model deployment, such as load balancers and auto scaling, and some of the container orchestration features that Abhishek showed in the demo. Those are all outside of Triton, but you can leverage Triton within KF serving or Kubeflow.
Yeah.
Yes. So let me add to this point that in this system, in the system we have shown here, the recommender system, Triton allows for you to write a custom backend, which basically means that you can integrate your custom code with Triton and run with it. So with all other reason, with adding all to what Shankar already explained, basically one reason to use Triton here is that we have customized the backend of Triton to run this custom this recommender system. But I believe there is also another question before that. How do you send a new model to the Triton instance running in GKE? I think we can say a little bit more about the deployment component. Abhishek, you already explained that basically there is a version number in the model that you deploy in the repository where Triton is looking for new models, and that allows Triton to pick the most recent model. But we can maybe tell a little bit more how the deployment component is implemented here.
Yeah, sure. If you don't mind, I can again share the screen and show it on GKE console itself. Yeah, so I have a simple bash pod running here, which interfaces the PV where we have the model stored. Yeah, so over here, I have the models at this location. Models. Yeah, so I have these three models which are specific to huge CTR. So basically for the recommendation system that we worked on, it was an ensemble model, which does both pre-processing as well as the final inference as an ensemble. So here you can see this model repository, which is passed to Triton, has three main folders. So here individual model folders. So for example, if you want to have a CV specific model, you will have one folder to that specific model. If you have a NLP specific model, you will have another folder to that specific model. And within each folder, so if you go inside this folder, there'll be a version number. So for us, we have model version 1. Like this, you can have multiple model versions. And that's exactly what we did in the demo as well. We after the pipeline is triggered again and model is retrained, we created another version, another directory here called directory 2, for instance, and that had the retrained model. So Triton by itself checks for the most updated version of the model and gets that for inference.
Abhishek, where was the model repository stored?
So the model repository was in a PV location on a network file storage.
Okay, so when the training ends, the checkpoint is copied after validation to the model repository, and then
Correct.
Triton automatically. Okay.
Correct.
Yes, Shankar.
Sure. There's another question. I'm going reverse order. Like, does this whole solution fit on an edge embedded device, or would retraining have to be offloaded? I guess the general thing would be it would depend on the memory footprint. I'm not sure if Abhishek, Davide, can this whole Merlin fit in an embedded edge, or does it need to be? I'm not sure what the memory footprint is. It depends on that eventually.
My answer would be no, because usually, especially the training for sure, no, because again, I would say the data sets are huge. We are talking about terabyte up to petabyte of data. Inference, on the other side, it may, I don't know for recommender system, I'm not sure, but I'm sure that there are computer vision solutions that runs on embedded and on small devices with TensorRT and with Triton.
For specifically in the inference use cases, we do have a lot of organizations and customers deploying Triton in embedded devices at the edge. And so, as Davide mentioned, that's certainly possible. Triton has this C API that allows you to directly integrate it into your application if you're running an embedded or edge applications. And so that way you don't have to make gRPC or HTTP calls, and you can avoid that network overhead. And also the Triton container itself comes with many different backends that are shipped in it, including TensorFlow and TensorRT and PyTorch and the others. But the container is customizable, so you can remove backends, and so you can reduce the size of the Triton container so that it fits within your embedded device.
Great. Thanks, Mohan and David. So I think the other question, I'm not sure if you've answered it in the chat, is how do you implement the monitoring component during a recurring run? How is the test data generated for real-time streaming?
Yeah, that's a good question. That's a really good question. So Abhishek, maybe you have more details on that? Okay. He got disconnected. Okay, let me start answering this question, and when Abhishek is back, he may add more on my answer. So let me start on how is the test data for that generated for real-time streaming data. So, okay, this is a recommender system, right? So once we compute the inference, so the recommendation, we'll send the recommendation back to the client. Now, at this point, let's say we are recommending movie titles, right? Now the user can pick a different title. So this data is collected from the client and sent back to the monitor component. Now, the monitor component knows what was the original inference recommendation. So it can tell actually that the recommendation was wrong or was not accepted. So this is new ground truth that can be first added to the original dataset for the next retraining or fine tuning, but also can be used to compute how the system is performing at the moment. And basically, what we do, the original dataset is split into test data and the metrics that we are using to compare the real-time performance are compared with those during training. So now, how do we trigger the retraining? Basically, we are using a publisher subscribe mechanism in Kubeflow that allows to generate an event to which basically the training pipeline is subscribed. And so when this event is generated, the training pipeline will trigger a new fine-tuning or retraining if required. So now for the details, of course, all the details of the implementation are in the script that we are releasing, and I'll add the link to the scripts at the bottom of the chat. And yes, this is the amount of details I have. Maybe if Abhishek is not back yet. But anyways, I will add the link to the script to the chat.
Thanks, David. I think that was another question we were replying on the chat is, can the ensembles be used to connect several models, or is it just for pre and post processing? And the answer is yes, it can be used to connect several models. And these models can all be different deep learning models, or they can be pre and post processing. It has the flexibility. In fact, you can also instruct Triton to run these models in different, like you could have one on GPU, one on CPU. So you have the flexibility of structuring this ensemble. Okay, Abhishek is back.
Sorry, I had some internet issues.
Yes, I was answering, Abhishek, I was answering the question about the monitor, the drifting in the real-time data. I described how we collect new data from the client. Maybe we can also describe a little bit how we monitor drift in the data, in the inference requests, in the features of the inference request.
Yeah, so over time for recommendation model data itself, the data distribution might change. So inherent statistics might change over time. So for our use case, we used TensorFlow data validation, which collects a lot of statistics about the data, which we can use to compare with the training data that we use for training the model. So model will perform well if the incoming data statistics or the distribution is same as that of the training data or similar to that of training data. If it's way different, then we need to flag that off, because inherently the model performance might go down on the incoming data, and the model might not know the new trend that's there in the incoming data. So we mainly use TFDV for collecting these statistics and comparing with the training. But there are other libraries called Selden and Alibi Detect as well, which can be used.
Great, thanks, Abhishek. By the way, there is if you go to the audience, if you go to the poll section, we have a few questions we'd love to get your answers to. One of the things that, as a team, what we are striving to do is, how can we make it easy for everybody to deploy models, regardless of the infrastructure, regardless of the frameworks? That's been the design, the whole philosophy of Triton. So if you can help us answer some of these questions, and that would help us, look at what kind of features and improvements that we should be looking at for Triton. Thank you. I don't think there are any more questions. If there are any other questions, please put it on the chat. If not, thank you so much for joining. And I think the links are being pasted in the chat. Please feel free to go try out Triton, try out the Merlin pipeline that we just demoed. And if any questions, you can obviously, go to GitHub and you can open an issue or contact us.
Just one other question there in the chat just now was around a question around how to implement glue code that might be between different models in an ensemble. So Triton has, as Davide mentioned at the very beginning, we have this concept of adding custom backends in Triton. And so you can think of a custom backend as either an entire new framework that you want to integrate into Triton. So for example, you might have your own version of TensorFlow or PyTorch, which you've developed specifically for your models. You can integrate that as a custom backend in Triton. For example, we worked with the Microsoft team to integrate Onyx Runtime as a custom backend in the beginning, and then it was productionized, and now it's available in every Triton release. So that's one concept of a custom backend. Another concept, though, is the same API in Triton that allows you to be able to integrate backends and different frameworks is also the same API that allows you to be able to integrate any kind of custom glue code or business logic or pre and post processing operations within Triton in either Python or C++. So I think the key kind of requirement is that it has to be in those two programming languages. But the same backend API allows you to be able to integrate any kind of glue code you want. And you can implement those in the ensemble around your neural network. So you can have some pre-processing or glue code, you have your neural network, and then your post-processing or other types of business logic. The other thing I'll mention is that the ensemble that we have in Triton was designed to optimize for throughput. So when a single request comes into the pipeline, it's going to trigger the execution of the entire ensemble at once. So that way we can minimize the overhead of having to transfer intermediate tensors or making multiple calls between the client and the server. And we're also working on enhancing the ensemble to allow you to be able to more easily add conditional logic. So if you need to do some kind of control flow where you have parts of your ensemble calling into other parts of the pipeline, we'll have the ability to programmatically express that logic through Python or again, C++. And so it allows you to be able to create even more complex ensemble use cases. But for the one that you described here with the glue code, that's already supporting Triton. You can already do that today. And you just use the backend API, which I'll provide a link here in the chat.
Great, thanks, Mahan. All right, looks like that's all the time we have. Thank you so much for joining, and we welcome you to try Triton, and please feel free to connect with us if you have more questions, or if you'd like to follow up a deep dive. Okay. Again, thank you very much, and thank you everybody and the presenters too.
Thank you.
Yeah.